By the end of today's video, you'll know how to have a robot that has a rotating turret on top be able to auto-align towards a fiduciary marker like an AprilTag.
You can move quite quick left and right and still have it auto-track.
I'm Brogan Pratt, and I've been teaching robotics design for over a decade now. We're going to start by walking step by step what is a PID controller, and then I'll also do a quick flowchart math for how you can set up a PD controller for rotating a turret towards a target. I'll show you how to program some of this in Java, and then we'll do an actual PD controller tuning session together. I'll give you lots of tips and tricks for how you can tune this to be better aligned as a system. Now, a few caveats on this. I'm going to be using FTC Java as a example. However, this will work, and this logic works for any system. The only thing you need to be able to pass in is know where your angle is in relation to your target. So you could use a Limelight, you could use a standard webcam, you could use a HuskyLens, you could use whatever programming language you want, C++, you could be using Java, you could be using Python, JavaScript. Doesn't matter what your robot is or what your platform is, the logic of a PID controller remains the same. Also, another caveat on this, this is a tutorial just on how you might rotate a PD controller. It does not include any safeties, so to speak, to stop you from rotating fully 360 degrees around. So if you don't have a slip ring on your system, I'll give you some suggestions on how you might add some safeties to your system so you don't rotate too far and end up ripping cables out of your turret as time goes by. However, with some time constraints, because this is going to be a bit of a doozy of a tutorial anyways, I didn't want to include those because it's just adding up too much information inside one tutorial. So before we can actually get onto the Java code, we have to understand how does a PID controller work. If you are familiar with PID controllers, skip forward to the next chapter. We can actually talk about how this PID controller is going to work for the turret. Otherwise, here's a quick explanation of what a PID controller is. So for our turret, effectively, we need to find a way that the farther away we are from our goal, the faster we need to rotate the turret back. And the closer we are to the goal, the slower we need to move that back. That's the basis of proportional control. So for example, if looking straight on is my goal, and I'm currently looking over here, the further away I am, the faster I should go. The closer I am, the slower I should go. So proportionally, how far away we are from our goal, we should be increasing and decreasing our motor speed. We're actually not going to use integral inside of this or I in that PD on that PID controller. So we're technically going to make a PD controller. And what a derivative control does is it allows us to add some damping force. So as we're further away from our target, we can damp it a little bit slower. So we might start going really fast, and then we damp slower onto the target. The higher derivative is, the more of that damping force gets applied to the place on. How derivative works as opposed to being proportional, where you're looking at how far away from my goal. If I'm really far away, apply lots of power. If I'm really close, apply a little bit of power. Derivative instead is applied based off a time base. So you might have reading number 1, reading number 2. If the readings are really far apart from each other, from reading 1 from reading 2, it's a large gap. That means you're still likely far away from your target because there's a large gap from reading 1 to reading 2. It means you're probably moving really quick from reading 1 to reading 2. So you should apply a low amount of damping on the derivative equation so that you allow yourself to still move quickly. But if this is reading 1 and this is reading 2, the distance between those two readings is far less than the distance between these previous readings, which means we must be getting close to our target because our proportional is starting to slow down, which means we actually apply more damping force. An integral is the sum of adding up over time. And in this case-based setup, where the more amount of time that we are out of alignment, we should have a much higher spike, is actually going to end up making our system less consistent than being more consistent. So a PD controller is totally sufficient for arriving on a turret. Because we're going to be using a PD controller, we're going to set this up in a class-based system to make it far more robust so we can import our own mechanism in. First thing we have to do is we have to be able to get some sort of time. So we're going to get our time from our last loop, and we'll get our time at the start, and then we'll reset it right after. So by the time we get up to the top of our next loop, our time is being reset. So we're going to say that dt, or delta time, is equal to elapsed time, and then reset timer. So that's the first thing we have to do. Then we have to check if the April tag that we're looking at is actually a valid ID. So valid tag, is it a valid tag? If it's false, we should break. and we should set motor equals 0. So we do not want to move the motor if the tag we're looking at is not true. And then here we're also going to set our last error to 0 as well to prevent large derivative spikes. We'll talk more about what that means later once we explain through this. If we do have a valid tag, now we can actually start with our P controller. So we need to get our error, and this is equal to our goal minus our current TX. And our current TX is whatever angle we are facing. If you're using a standard webcam, it's likely returning you a bearing. If you're using a Limelight, it's likely returning you a target X. If you're using a HuskyLens, it'll also return you I believe it is a bearing based off the blocks. Once we know our error, we can actually create our P term. So our P term is equal to our error multiplied by our KP to be able to find our P term. So that is how much proportional control we're actually going to apply. Next up is time to actually apply our derivative term. So we're going to check is dt greater than 0, just so we don't have dividing by 0, just in case. If it's false, we're just going to set d term equals 0. Otherwise, our d term is equal to our error minus the last error divided by our delta time, and then we're going to multiply this by our KD. And this is how we end up finding our D term. Next up, we want to check, once we have our P term and our D term calculated, we need to check if our absolute error is within some sort of tolerance. So for example, when you're doing this camera-based system and vision, and you're trying to rotate towards a target, rarely do you ever want to be exactly on the target. And particularly for a lot of these designs, and it depends on how accurate you need to be, but for the most part, being within half a degree of accuracy is good enough. So for instance, if I'm looking at the camera right now, you might say this looks directly at the camera. You might say this looks directly at the camera. You might say that looks directly at the camera based on how far away I am. That was about a 2-degree difference or a 2-degree tolerance. Whereas we know that if I'm way over here, it's probably too much. So you want to have some sort of a dead banding zone where you're actually happy with that amount of tolerance. So what we can do is we have another decision. If the absolute of our error is less than our tolerance, if this is true, then our motor equals 0, so that we are not rotating our motor anymore. If it's false, this is where we can actually apply our P term. And here we're simply going to say a clip of P term plus D term, and we're going to clip it between negative 0.4 and positive 0.4, depending on how much your rotation is. And the higher you make these values, the faster you can rotate, because for a lot of these systems, you don't actually want to be rotating at 100% power of your speed or for your motor. Depends on how fast of a motor you're using and how much of an RPM of the motor you're using as well. Then the last thing you're going to do, and actually I forgot to mention here, this is going to be power equals this, and then we're just simply motor equals whatever the power is, whatever our speed is, and then our last error is going to equal error, so that we end up are able to do our derivative equations later. So going through this flowchart really quick and how this ends up working, at the start of our loop, we get our current time for the delta time, and then we reset our timer. By the time it gets all through this loop and we get back up to the top of the loop, it'll tell us how much time has passed between those two different readings. So that allows us to be able to get what our current time is now versus the previous last time we checked. Our delta time is the change in time. Then we need to check, is the tag we're looking at perfectly valid? If it's not a valid tag, we should set our motor to 0 because we don't want to be rotating. We should also set our last error to 0. What happens if we don't set our last error to 0 here is that we can end up calling it a derivative spike. So if we don't look at something for a really long time and all of a sudden we look at it, that means that the last time between our previous checks would have been huge, and our derivative is going to have this massive spike, and you're going to end up coming from big here and you're going to super overshoot. So that's what that last error does. If we do have a valid tag, we're going to set our error to our goal minus our TX. That's our current bearing away from it. Our P term is error multiplied by KP. Then we check if our delta time is greater than 0. It's potential that it is. If it is, we just simply set our delta term to 0 because there's going to be no derivative. Or sorry, not delta term, derivative term to 0. If we are greater than 0, now we can actually do our derivative calculation. We take our error minus our last error divided by delta time, and then we multiply that by our KD. And then we come down, we check, is the absolute error less than that tolerance? So are we within that tolerance angle for directly looking at the target? If we are, we turn our motor off because we don't need to keep rotating for directly on. Otherwise, we then take a look at our system. We say, okay, our power is equal to a clip or a clamp of our P term plus our D term, but the maximum value we can ever rotate is, negative 0.4 to plus 0.4. You're gonna have to tune this. And then finally, we set our motor to that power, we set our last error to error, and then we break out of our loop. Now, one final caveat I forgot to mention. Right here, in this current setup, there are currently no safeties on that system. So it's entirely possible that we could spin around in a full 360 degrees. Works great if you have something like a slip ring for your system, where if you have any electronics on your turret, it's able to rotate around and you can transfer through that power and there's no issues. If you don't have a slip ring on your system, you can probably tell the problem that's going to pop up now. If you have a wire hanging on your cable as you rotate around, you're eventually going to get to a point where your wire is actually going to get caught. So some ideas for how you might do some of those is you could use an encoder on the motor, and once the encoder gets to a certain tick, you're no longer able to rotate past, and then you'd have to rotate yourself manually back in order for the P controller to get plugged back in. So that could be a quick safety before you actually do a motor power as well. You could also have a magnetic limit switch or a standard limit switch on it so it can't rotate around. You can have a physical stop with a sort of hard beam. So when you hit into that beam, you just physically can't rotate anymore either. So that's another option for ways that you could make the system a little bit more safe. But again, as I said, this isn't a tutorial to teach you how to do all of these things because I think that that's too many skills to build into one tutorial. So that is roughly how our P controller is going to work. Let's go take a look at how this is actually going to turn and translate into Java code. All right, so let's start with making the actual turret mechanism class. I always prefer to put these things inside of classes so we can reuse it across different op modes and then also keep our code a little more encapsulated. It's just a good programming practice. So let's start by making a new class. I'm going to call this one turret mechanism tutorial. Of course, you could call it whatever it is that you want. Now, the first thing inside we need to do is we need to be able to create the motor that's actually going to rotate the turret. In my case, I'm going to be using just a standard DC motor. So I'm going to make a new private DC motor X, and I'm going to call this one called turret. And now it's time to set up all of our different constants that we're going to be using for our PD controller. So we're going to make a private double called KP, and we're going to set this one to something really, really low at the start, something like 0001. We're also going to make a private double called KD. We'll set this one to something even lower. Actually, we're going to just start it at 0 because we're going to tune KD later. We're going to make a private double called goal X, and we're going to set this to 0 because we want our goal to be directly pointed at the target aligned. Now, it's possible that you might directly align your camera on the target, but you actually want to shoot offset to the right slightly. So in this case, you could set your goal to a negative offset or positive offset, because what you'll also likely find is sometimes based on your distance to the target, you also need to have a slightly different offset for this as well. So this allows us to sort of tune our goal X as time goes by. We'll also have a private double called last error, and we're going to set this to 0. We're going to have a private double called angle tolerance. We'll set this to something like 0.2 degrees. The more accurate that your camera is, the higher or the lower your tolerance can be. And the further away you are from your target, the lower your tolerance should likely be as well, because the closer you are, an angle doesn't sort of propagate out near as far either. We'll also make a private final double called max power, because we only ever want our turret to be able to rotate at a certain point. I might set 80% for mine, you might set 60%. You're going to have to tune that. I'm also going to make a private double called power, and we're going to set this to 0, and that's what we're actually going to change so we can actually rotate our turret. And then we also need some sort of timer to track this as well. So I'm going to make a private final elapsed time called timer, and this is going to be a new elapsed time object. So this allows us to just keep track of how long it's been in between loops. Now we need some sort of initialization method so we can pull this into other classes. So I'm going to make a private void called init, and I'm going to pass in a hardware map of hardware map. And inside this, we're simply going to initialize our DC motor. So our turret is going to be equal to a hardware map, hardware map.get, and it is going to be a DC motor x.class, and I'm going to call this turret in my case. Whatever you have for your setup, you just make sure that your configuration file has it actually labeled as so. And then because we're going to be using our own P controller to be running this, we're going to say our turret.set mode, and this is going to be run without encoder. Now this will still allow us to read encoder ticks, but it is allowing us to create our own P controller for the robot, for that motor specifically. Now, in order to be able to tune our setup here, we want to be able to change and modulate our KP. So we're going to make a couple getter and setter methods. So make a we're going to make a public void called set KP, and we will pass in a value of new KP. This should be a new double of KP. And then we're simply going to say that KP is equal to our new KP. We'll also have get what our current is. So we'll say public double of get KP, and we'll just simply have nothing, and then we pass in, and we'll just simply return KP. We'll do the same thing for our KD as well. So we're going to set KD with a new KD and a new KD. And we'll do the same thing with our get KD, just to be able to protect our proportional and derivative constants a little bit better. Now we also probably need some way to be able to reset that timer at the start of our main loop. So we're going to make a public void called reset timer. We're going to pass in nothing, and we're simply going to say timer.reset. And this will just allow us to reset our timer at a certain point, because when we start our code, we want to make sure that our turret's timer is the same starting point as all the other timers inside of our system. And now comes time for that actual logic. So we're going to make a public void called update. And inside of our update method, we actually need to pass in an argument. And this is going to be what our current fiduciary marker is. So you could either just pass in your target X, you could pass in whether the tag is null or true, whatever have you. I'm actually going to pass in an April tag detection called CurID. And this is an object that basically returns what the bearing is, what the yaw is, what the target X away is, what the target Y is away, and so on. If you were using a Limelight, you'd pass in a Limelight result object. You'd pass in a networking table depending on how it is that you are setting your system up. Because I'm just using a standard webcam, I will use that in this. First thing we do is we're going to set a double called delta time, and we're going to set this to timer.seconds, and then we're going to reset our timer. So timer.reset. So this allows us to keep track of how long it was since our previous loop, and then reset it so that by the time we get back up to this update method, we can know how long it was for that derivative control. Now next, I'm going to check if CurID is equal to null, because in my method, I only pass in the object, or I only call this if it actually is going to be a valid object, because I only have one ID that I'm looking at. For this tutorial, only AprilTag-20 is acceptable. You may also have to add in some sort of check in here. And CurID.ID is equal to 20, whatever that ends up being. I'm actually not going to do that because I only have one valid ID. I'm going to then do turret.setPower, and I'm simply going to set our power to 0. I'll set our last error to 0, and then we will return and then break out of this update loop because we haven't got a valid ID. If we do have a valid ID, this is where we can actually start PD controller. So first up, we're going to make a do double called error, and this is equal to our goal X minus our current bearing away. So in this case, it is CurID.ftcPose.bearing, and that's going to give us our direction, sorry, our angles off the target. If you're using Limelight, it might just be your TX. Then we have our double of P term is equal to our error multiplied by our KP. Oops. KP. And that is our proportional control. Now let's start getting into our derivative control. So I have a double of D term is equal to 0. And then if our delta time is greater than 0, just to check that we're not dividing by 0. Now, in practice, you're probably never going to have a loop that's going to be exactly 0 parsing through. You're always going to have some sort of really long floating point number, but it doesn't really take any resources to really do check this, and it's a good safety and good practice. Then we can set our D term is equal to our error minus our last error divided by delta time multiplied by our KD. Then it's time to check if we are within our angle tolerance. So we're going to say if the math.absolute of our error is less than our angle tolerance, then we're simply going to set our power is equal to 0 because we don't actually run our motor. Otherwise, we can actually do our main equation. So else, oops. So we'll say else our power is going to be equal to range.clip, and this is going to be our P term plus our D term, and then we have our negative max power and our positive max power. Now, as I said before, this is not a tutorial about how you could put in safeties here, but here you could probably do a safety encoder check or magnetic limit switch check or other safeties so that you are not rotating past your current target. But in any case, now we can simply do our turret.setPower to a value of power depending on what was actually calculated above. And then our last error is going to be equal to our current error. So that we can set that up for our next derivative loop. So this update method is what we're going to call every single loop so that we can actually update that turret and so that it knows where its current state is and always be aligning. Now with that set up, let's actually go ahead and use this in example OpMode. So I'm going to make a new Java class here, and I'm going to call this one turret auto align OpMode tutorial. And we are going to extend the standard OpMode. You can extend linear OpMode for this. I prefer standard OpModes just because it allows you to write things like state machines a lot simpler, which is a far better use case in robotics over traditional linear programming. So inside every single standard OpMode, we always need a public void init, and we need a public void loop. In this case, we're also going to have a public void start in this case as well, because we're also going to have to call something when we push that initialize or we push that start button for resetting our timer. Now, as usual, you need to have some sort of April tag set up here. So I'm going to have a new private April tag webcam called April tag webcam is equal to a new April tag webcam. And this is just a helper class that I set up to be able to do some different April tag class-based methods. So in my case, this is using snap webcam. You could do your Limelight, whatever have you. We're also going to have to make a new private turret mechanism, and we just called the turret mechanism tutorial called turret. And this is going to be a new turret mechanism tutorial. And now that we have our new objects set in here to be able to get our camera vision as well as getting our turret mechanism in here, let's go ahead and actually run those initialization methods. So for my April tag webcam, I need to call it an init method, and I expect a hardware map. I also expect a telemetry object inside there as well. Oops, and that should not be capital. And then we also call that init method we just made inside that turret mechanism. So I'm going to say turret.init, and we need to pass in a hardware map for that init as well. Oops, that should be a public void. I definitely made that a private void for init. It definitely should be a public void for init. Now, I always like to give myself some sort of feedback to let it know I've actually initialized. So I'm going to say telemetry.addLine, and we're simply going to add in initialized all mechanisms, just so that we know that we're ready to rock. Now, if you remember at the start, we need some way of making sure that our turret's timer is set back to 0. So when we start this, we're actually going to say turret.reset timer, so that when we're starting up our loop, our turret also starts at the same 0 point as our loop actually does. Now, the first thing you need to do is you need to run your vision logic. And in my case, it's going to be AprilTag webcam.update. And then I also have, AprilTag detection of ID 20 is equal to our AprilTag webcam.getTag by specific ID, and I can pass in the ID that I want to actually grab. This is why I did not handle this logic inside of our turret mechanism where we want to check if our current ID is, because the specific ID that I can search for is already handled inside my AprilTag webcam. You're welcome to do it in either. I prefer to have those specific logics handled inside of the webcam and then paste that in, but it is, a 6 on one, half a dozen the other kind of deal. So then we can call our turret.update and we can pass in our ID 20 because that is our AprilTag detection. Again, you could pass in, your TX, whatever it is that you're using, pass in your fiduciary marker object or just standard target X. And then last up, we'll add in some telemetry. So I'll say if our ID 20 is not equal to null, then we can have a telemetry.addData. And we'll simply call in our cur ID, and we'll pass in our AprilTag webcam object. And then else we will add in telemetry.addLine, and we'll say something like no tag detected, stopping turret motor. And that's your base Java code. Now, presently, we don't have any way to actually tune this Java code so that we can actually tune our KP and our KDs. So if you followed through some of my tutorials in the past, you may have seen this before, but I'm going to show you an easy way that you can actually start tuning your KPs and your KD based on some gamepad inputs. So I'm going to make a quick list here called step sizes, so I can have different step sizes to be able to increase my KP or decrease my KP from. And then we're going to start initially at a not 1 value. Then before we do our telemetry statements here, this is some code that's going to allow us to update it on the fly. I can press the B button to be able to cycle through my step index, so I can increase it by 0.1, not 0.1, not 1, whatever that ends up being. If I press the left D-pad, I can set the KP based off that distance. I can add KP if I press the right D-pad. If I press up, I can add to the KD. If I press down, I can take away from the KD. And this is just using our turret.set KP, get whatever the current KP is, and then subtract what our current step size index is, so we can pull off of that value. And then, of course, when you're tuning, it's always nice to have some of these telemetry updates. So what I'm going to do is I'm going to have our tuning KP up to 5 decimal points to be able to rotate left to right, and then we're just simply get whatever our current KP is, get whatever current KD is, and then get whatever our current step index is. So this will just allow us to be able to tune some KP and KD on the fly. Now let's go over and let's actually start demoing this, because tuning a PD controller is as much an art as it is a science, and I'm going to try to give you some of the best tips that I can. Now, one thing I'm going to add in here is I'm going to add in a quick mechanism drive chassis so that I don't have to physically rotate my turret, and I can just use my controller to be able to drive that around. So I'm going to go add that in quick before we get onto that tuning. So taking a quick look at my setup here, I simply have a piece of steel here mounted to a motor with a Logitech. I believe this is a 270 or 720. I can't remember what the name is. It's C something, C270, I think. And this is a 312 RPM motor with basically nothing on it. So this thing should be able to whip around pretty quick. And I have AprilTag 20 set up probably about 2-ish meters away from my robot here. This does work a little more reliably with a camera that has a much wider field of view. So I actually can't rotate super fast with this, simply because the time that it takes for the AprilTag to process on board on the control hub slows down my loop time, so I can't actually get this going really quick. Whereas if you were to have some offboarding on this, something like a Limelight camera with much higher FPS than the C20 or 270 is set up for, you'd likely have more success with the speed of your rotation. So keep that in mind in this tutorial. Now, one thing I also want to mention about this system here is there's a lot of backlash in this system. So this is the motor actually not rotating. And we can see that we can probably have a few degrees of backlash just in the motor itself. So you might want to add some sort of spring tension system to try to remove some of that backlash, or find a motor that has a little less backlash than this system does. Because in order to get pinpoint accuracy on this, I'm not actually going to be able to hit those tolerances that I need based off of how much backlash I have. So let's go ahead and set up our, I believe this is the turret auto align auto. We'll go ahead and initialize this, and then we'll go ahead and boot it up. Now looking at this, what I can do is I should be able to rotate my robot to the right, and we should have this start auto lighting. Now it looks to me that it's presently not auto aligning because we can hear that coil whine. So what that tells me is if it's not auto aligning, that our P is a little bit too low. So if I use left and right, I can actually start increasing my P, and we can start seeing that as I rotate, it wants to kick a little bit, but it doesn't have quite enough P value. So I'm going to go ahead and increase that P a little bit more until we actually start rotating towards our target. And that is starting to be more on the path of what we're looking for, but our P is still a little bit low of 0.05. So let's go up to something like 0.1 and see what that looks like. So that looks more along the lines of what it is that we would expect for a P value to be auto adjusting. Let's go ahead and flip ourselves back. And like I said, I won't be able to rotate super quick because my value won't increase. So let's try increasing our P again. Oops, that was D. And what we want to see is we want to get to the point where we actually start overshooting our target. So let's try, not 0.02. Because we want to be out, there we go. So we can see that at that point, we actually overshot our target, which is not what we want, which means our P value is far too high. So let's actually bring this down to, 0.016. And let's see if we can bring this back. It does, again, look like our P value is probably too high, again, because we're starting to overcorrect. So let's bring this down again to something like 0.12. And that might be too low now, because as we rotate, it's not quite getting at the right speed that I would like. So maybe let's try 0.14. We get to the point where we get a nice little bit of moving, but not so much. And that's actually pretty solid. We're getting a little bit of overcorrection there. So as I turn quick, you can see we get a little bit of overcorrection. It's probably still too much overcorrection, actually. So maybe I'll try 0.13. We can see that it actually wants to bounce forward and then back. All right, so now let's actually start doing our D value. So I'm going to actually bring my step size down, and we're going to increase our D value to 0.0001. And we're going to look to see what that damping is. And we see we're actually sparking left and right, so I'm actually going to do 0.001, because I find that these systems are very sensitive to D value changes. So we can actually see we're still overcorrecting a bit too much on that. So let's move just a bit. And it looks like our D value is still probably a little bit high. So I actually might need to go back and change my step sizes, because I don't believe that I have the ability to do a step size any lower than 4 knots. So let's add in an additional step size here. Okay, so I've now got and I forgot to I forgot to increase the size of my formatting for that step size to be able to show 7 different points, but I actually can't show 7 different points at the moment. So I actually have a D of 5 zeros and then a single 1 here. And this one's actually pretty solid to have a much lower D. So you need really low derivative. And we can see that as I actually rotate left and right, that the Limelight, or this is not a Limelight, sorry, this is an AprilTag. It is capable of auto-tracking itself as I move left and right, and it's able of updating itself looking at the turret. Now I will say that the hardest part of this is you can move quite quick left and right and still have it auto-track. The hardest part of this tuning is rotation, just because rotation stresses the system so much more than just simple left and right tuning does. And my P value might still be a little bit high here. But realistically, you could tune your P and your D controllers until the cows come home. I think the purpose of this tutorial here, that's good enough to be able to get you off the races where you can do your own tuning. Effectively, you want to be able to get your P up to a point where you're not overshooting your target. My P is still a little bit high and I am overshooting that target. Also keep in mind, if you use a different motor setup than me, you'll probably end up with different KP values and different KD values as well. If you're looking for this code as a code snippet that you can put into your own robot, you can consider joining my community down below. I've got lots of different robotic resources, CAD files, code snippets, things like that, as well as some additional tutorials and resources that I supply from my members. If you got any questions about this tutorial or something wasn't clear, let me know in the comments down below and I'll do my best to try to answer them for you. And as always, best of luck out there with your next robotics project.